Hello everyone, my name is Satvik Ganesh, and for today's presentation, I'd like to talk about my work titled FSPC, a lossy spike compression through correlated AER merging in spiky neural networks. So let us begin. So here's the content for today's presentation. Let us start with the background, starting with spiky neural networks. Spiky neural networks, or SNNs, are the third generation of neural networks that are designed to mimic biological neurons and use spikes to convey information. The figure below shows the structure of a typical SNN. Next, I'd like to talk about the leaky integrate and fire or LIF neuron. The figure on the left shows the LIF potential dynamics, whereas the figure on the right shows a typical SNN neuron. On the left figure, it can be observed that the potential increases with input spikes. However, it leaks through time. But when the potential reaches a threshold, an output spike is generated. On the right figure, we can see that the dendrites take in the input spike trains, and the axon emits the output spike trains. Now, I'd like to discuss rate coding, which converts input intensity into spiking frequency. Here, the pixel intensities are used to generate spikes. As you can see in the following figure, a black pixel of input intensity 0 produces no spike per time step, whereas a gray pixel of input intensity 0.5 has a 50% chance of a spike generation per time step, whereas a pure white pixel of input intensity 1 has 100% chance of a spike generation per time step. Next, I'd like to discuss address event representation, or AER in short. It is a neuromorphic protocol for encoding timing and location of spike events, and it only conveys the timing and location of active spikes as shown in the below figure. Next, I'd like to talk about pattern mining algorithms. They find interesting and relevant patterns in the dataset. Now I'll discuss two pattern mining algorithms, FP growth and FP max. FP growth compresses the dataset into an FP tree to directly extract frequent patterns. FP max, a variant of FP growth, uses the FP tree with pruning to find only maximum frequent patterns. Now I'd like to discuss the motivation. Rate coding is simple and noise resilient, but it generates higher spikes, which lead to higher energy and latency. This limits the scalability of SNNs in resource-constrained systems. This is something that we observed during rate coding. We found that some neurons fire in groups at the same time step, as shown in figure 5. We found that highly similar spike patterns were observed at time steps 4, 9, and 18 in the hidden layer. Upon doing similarity calculation using Jacquard, we found 30.5% spike similarity, which indicates temporal, moderate, high temporal redundancy. With regard to this, we make the following contributions. We propose frequent spike pattern compression, or FSPC, which is a framework for compressing co-firing neuron activity in SNNs. It leverages pattern mining algorithms to identify neuron sets that frequently fire together. And then these co-firing sets are merged to reduce the overall spike data size. Now, I'd like to discuss the proposed method. There are two key steps, pattern finding phase and compression phase. So here, the figure on the right shows the overview of the FSPC framework. Now, I'd like to discuss some important terms that we'll be using in the upcoming slides. First being frequent spike pattern, or FSP. These are a set of neurons that fire simultaneously at the same time step. Pattern match threshold, or PMT, is a floating point value from 0 to 1, which defines the minimum proportion of FSP neurons that must appear in the AER data for a valid match. The required number of FSP neurons in the AER data is calculated by the following equation. So here's the location of FSPC in SNN. As you can see, it is located in the hidden layer between layer ln and ln+1. We'd also like to note is that this framework works during the inference phase of the network. Now, let us start with the pattern finding phase. First, we extract the spike tensor from the previous layer ln and encode it into the AER format. Next, we extract the FSPs using pattern mining algorithms and assign them symbols, as shown here. Next, we find the presence of FSPs or the location of FSPs in the AER data, as shown here. Then, in the compression phase, we compress the FSPs with symbols in the AER data. Next, these compressed symbols are decompressed with the corresponding FSPs in the AER data. Afterwards, we decode the recovered AER back to the spike tensor and we send it to the next layer ln+1. Now, FSPC supports both lossless and lossy compression, and this is controlled by the PMT value. A PMT value of 1 indicates lossless compression, whereas any value less than 1, such as 0.7, indicates lossy compression. It should be noted that at PMT 0.7, the pattern at time steps 2 and 7 will be also taken because at least three elements of alpha 1 are present. Now, I'd like to talk about the results. Here's the setup that we used. This is the model configuration. We used MNIST and Fashion MNIST datasets for testing. We used SNN Torch framework for building SNN models. We used the following pattern mining algorithms: MLXTEN FP max, PAMI's FP growth, and max FP growth. And this was the minimum support value that was calibrated for these pattern mining algorithms. Our evaluation criteria was based on PMT and FSP. Now let us look at the evaluation based on FSP. The left vertical axis shows the accuracy, whereas the right vertical axis shows the compression for both MNIST and FMNIST dataset. For the MNIST dataset, we can see that the average accuracy drop is 0.2%, but for FMNIST, it is 1.16%. Talking about max compression, we see a 20.59% max compression on the MNIST dataset and 31.50% max compression for FMNIST dataset. Talking about accuracy, we see that when using FP growth and max FP growth, the accuracy keeps on falling, whereas in FP max, the accuracy stabilizes for MNIST dataset. However, the opposite is true for FMNIST. Now, we may do evaluation based on PMT. We see that with the increase in PMT, we observe 12.59% loss in compression MNIST dataset. And on FMNIST, we observe 15.29% loss in compression. Talking about accuracy, for all three pattern mining algorithms, we see that the accuracy increases, reaching to baseline levels when the pattern mining threshold increases. In conclusion, we proposed a lossy spike compression for SNNs. We saw on average 12 to 15% spike data reduction with 1 to 3% accuracy loss. This has the potential to improve simulation efficiency and support adaptive hardware-aware compression. In the future, we would like to integrate this framework into the training phase and develop faster and scalable mining algorithms. Here are the references. Thank you very much for listening.